So yeah, I'm here to talk about enumerables. My name is Brett. I grew up near here in San Antonio, but I'm more recently in Utah. I work at, like Nathan was saying, it's called Surge with my brother, working to build a better SMS API. And I enjoy cooking and baking. I'm looking for the perfect kolache recipe. Here's an attempt I've tried in the past, but if you have any tips, I'd love to hear them. Or if there's a place near here, I'd love to hear about it. And I've been working on Elixir for a while now, and I love digging into how stuff works. And one of my favorite things about it is enumerables, which is maybe a little weird, but to understand what's going on there, it's going to help to look at kind of how we got to where we're at. And so with Elixir, when you are looking to traverse a collection of items without something like enumerable, you're going to be doing recursion. And so there's an example here where you're trying to toString each item in a list, and you're mixing your concerns about traversing the list with what you want to do there. And so we kind of solved that with higher order functions. If you define a map function, for example, that worries about traversing the list, and then just lets you pass in what you want to do with each item, that lets you kind of separate those so that you can kind of get rid of the recursion, have something worry about how to get to each item, and then you can tell it what to do with each item. But just doing this for lists, then you have to do that for any sort of collection. So if you want to do it for maps, you've got to have a higher order function there, sets, whatever. And then you've got to do that for map, filter, zip, whatever operations you want to support. And so you end up with a big kind of cross product there of data structures by operations. And if you want to do one operation on a data structure that doesn't support it, you have to reach for recursion anyway. And so kind of the goal was to come up with a shared protocol for this is how we enumerate things. And so you just implement it once per data structure, then the operations can build on top of that and keep your area a lot smaller. And so in Elixir, that's the enumerable protocol. And a lot of this history came from a blog post that Jose wrote more than a decade ago called Introducing Reducees. And I'll have this link down at the bottom afterwards. But we started with kind of an iterator where you say, okay, give me the next thing in this structure. And if you don't have a next thing, tell me. And then if you want to build map on top of that, you can say, okay, give me the next thing until there is no more next thing. And so this is going to look pretty similar to the recursion, except now the next is kind of abstracted away from matching specifically on the list. And so that sequence will kind of look like this. So if you map over A and B and toString it, you ask, okay, what's the next thing in A and B? You get A, and you've got B left over. And okay, what's the next thing with B? That's B. Okay, what's the next thing on the empty list? Nothing, and you've traversed the thing. And that works pretty well, but there's not a great way to clean up after yourself. With lists, that's not a big deal, but Jose was concerned about if you're iterating over a file or running in a database transaction, and you stop working on that, you need to go clean up. And you could introduce like a halt on the iterator, but then whoever's calling it would need to remember to use it. And so he kind of looked at Clojure for inspiration on that. And so Clojure had more of a reduce, and so each collection would have a reduce function that would take an ack and a fun function, and works a lot like, Enum.reduce, for example. And so to do a map, you just say like reduce into this list, applying the function, and then once you've built up the accumulator, reverse it. And so that same operation built on reduce instead of iterators, you end up calling reduce, and the reduce just interfaces with the passed in like reducer function to build up your accumulator. Then the map reverses it, and that returns. And that's a lot more efficient. Lets the resource clean up after itself. But there's not a great way to stop early. If you want to just say, give me the next n items, the reducer is going to go through the entire collection. So Jose at CodeMesh 2013 was listening to a talk by Jessica Kerr and was looking at, and I don't know how to pronounce this, is it Scala Z-Stream? And was kind of inspired and dug into how that worked with some of the monad stuff. And they came up with a way to pass instructions up and down with the reduce. And so that kind of looked like you'd enumerate on something and then have like an instruction and a function. And so if you got like a cont with a function, you'd recurse and call, like I got this thing with this function, and that function call would return the next instruction. And I don't want to get too into the weeds with this part, but it lets you pass instructions up and down, let either the calling function or the data structure say, okay, we're done. But it builds a new function for every item in the reduce. And so maybe a little hard to see from here, but so when you call enumerate, you call function 1 with the first item, and it's like, okay, here's function 2. Call function 2 at the second item. Okay, here's function 3, and so on. And then when you say, okay, function 3, I'm done, it's like, okay, here's your accumulator. And that kind of solved the stopping early thing, but the accumulator was hidden in the closure, so it's kind of hard to reason about. And creating these anonymous functions for every item in the list, they were seeing 6 to 8 times slower performance than the reducers. And so they iterated it on some more to not create new functions, and ended up at what they called reduces, which is pretty similar to how Enumerable works now. So they would do reduce on the collection with that tagged instruction, but instead of a function passed there, you'd have an inner accumulator, and then you would just recursively call the reducer function with the item and the accumulator. And then if you continue to get cont, you keep going until you either don't or it's done. And if you get like a halt, you just clean up after yourself. And so the map ends up looking pretty similar to using it with a reduce, where you reduce over the collection. Your initial accumulator is continue with an empty list. And then each item, you say continue, apply the function, and stick it in the accumulator, and reverse it all. And so really the only difference in this implementation versus the others, you have the continue instruction and have to worry about the done. And here's the other function for reference. And so, yeah, with that, you end up doing the reduce, and it works pretty similar to the reducers we were seeing above. But we'll see in a moment, it lets you do things like take and stuff because you can halt in the middle. And so this looks pretty confusing, but this is the type spec for enumerable.reduce. And so you, it looks pretty similar to what we did up there. You have the enumerable. You have, it calls this ack, but it's your like instruction with the ack. So a cont, a halt, or I'll talk about suspend in a bit. And then your reducer function, which takes the element and your inner ack and returns a new instruction. And then the whole thing returns, okay, we got done, or you halted me, or you suspended me, and here's a function to continue. And so that's a little confusing, but if we look at the list implementation, it's going to look pretty similar to up above. And so if you get a halt instruction, you're going to say, okay, I've halted. We'll skip suspend, we'll just, yeah, suspend. You say suspended, here's my current ack. And if you call me with a new instruction, like this function will keep going. And then if we get an empty list with a cont, we say, okay, we're done. And if we get a cont with items still in the list, we do that recursive call to reduce again. And let's see, so if we look at the diagram for that, when we, so this is, I made a hack together library for tracing these enumerable calls, just where it's all function calls. It wraps each function and puts it into the process dictionary to kind of trace this. And so we have the list A to B, and then do an Enum.map on it, toString. And so we end up with something pretty similar to what we were seeing above. In range, it's going to work pretty similarly, but we can say, okay, if we get halt, we're halted, suspend, here's our continuation, and then the main bulk of it's going to happen here, where we say, if you're in the current range, here's the recursive call, and then if we're out of the range, say we're done. And then that, I guess I didn't trace that one. And so, yeah, this kind of shows you get the cont done. And then to show the halting, we can look at something like enum.take. And if you do a take of 2 items on this list of 3, we'll say, like the enumerable will call the reducer and say, okay, your first item's A, and here's the accumulator you gave me. It'll say continue, here's the new accumulator. And so it'll say, okay, here's the second item with that new accumulator. And then the reducer which is from the outside, will say, okay, that was 2 items, halt, and here's your accumulator. And so the list will say, okay, I've halted, here's the accumulator, and Enum.take will turn that into your list of 2 things. So it's a little work to think through, but I'm hoping the diagram is helping with this. And then the suspend is used for things like Enum.zip. And so for this example, I'm going to trace both ABC and the range 1 to 2. And when we call Enum.zip on it, it's going to reduce on the ABC. The reducer is going to ask for, or the reducer is going to be given, here's A, and it's going to be set up to say, okay, just every time you give me something, suspend. And so it'll say, suspend, here's the ACK, and that'll return to enum.zip. And so then it will ask for like the 1 item from the 1 to 2 range. And so it's kind of like the iterators we were seeing above, just kind of in this pattern, I guess. And so it can ask each of them for 1 item at a time, zip them together, and then at the end, it says, okay, give me the next item. Let's see. Yeah, so it'll say, give me the next item in the empty range, and the range will say, okay, we're done, like you've gone through the entire range. So zip will say, all right, halt the list enumeration, and that'll say halted, and then it will have zipped things together. And so that is kind of the main function in Enumerable, is just how do we reduce that. But then there's some optimizations for operations that you don't want to enumerate the whole thing. And so the first one is count. And so it's made for cases where you just want to see what's the size of this enumerable. And so with each of these optimization ones, you're going to return either, okay, here's the thing, or error, here's my enumerable module. And so the docs say, if you can count the number of elements faster than traversing it, should return okay there. And so, for example, the map implementation just says, okay, here's my map size, because that can be gotten in constant time. And so if we trace that, we see what's the count on that, and it just says, okay, 2. But if we do it with something like stream, it doesn't have a way to say this is the exact size of my stream without going over it. So it returns error, and this is in the stream implementation, so it'll be enumerable.stream there. And so if we trace that by just doing a stream.take to turn this map into a stream, and then run a count on it, enum.count will say, okay, enumerable, count this thing, and it'll say, error, here's my enumerable implementation, and then it'll do a reduce-based thing to count the items in that collection. Another one is member, and so similarly, you can check the membership without traversing the whole thing. You return okay Boolean, and the date range is a little complex looking, but essentially it can just say if this date happens to fall within this date range, we can tell that without going over the whole thing. And then if we run a trace on that, we can see that that's what happens. They like, is today in this week, and just get back true. But with a list, for example, and list will have a lot of like caveats. So a lot of enumerable will say, I can actually do this better for list than the enumerable implementation for list. But its enumerable implementation will actually say, you've given me an empty list, I just know whatever you've asked is not going to be in there. But otherwise fall back to the implementation module. And so you end up with kind of the same thing where it asks and is told, no, I don't have a more efficient way to do this, and falls back to a reduce. And then the final one's a little more complicated than the other optimization ones, but it's called slice. And it's gonna ask like, hey, can I slice you efficiently? And it'll say, okay, here's my size of the thing, and then either a slicing function or a toList function. And so the slicing function is the like preferred one, where you can just give it a start, a length, and a step, and it spits out a list at the range you want. But then there's also a toList function that you can have returned. And that seems to be, from what I can tell, preferred, because that gives you a size which Enum can use to like check the bounds. So even though it ends up having to drop all the elements before it in this toList, it still works out better for the bound checking, I think. And so if we look at the range implementation of slice, it's going to do the slicing function. It says, okay, here's the size of my range, and then a function that takes the start length. So start gets added time step to the beginning of the range. The step gets added to the other step. So the step of the range and the step of the slice. And then the length is how many items to take. And so it just lets you, come up with a more efficient way to do that. And so that trace is going to look like this, where it says, hey, can I slice this? And it's like, yeah, that's how many items you've got in the range. Here's the slicing function to get that. So it says, okay, I'm going to call that position with that step, or with that. With that length. So 2 items at position 234 with a step of 1. And so you can get those out a lot faster than enumerating over that. But you can't do that with something like a map set, but you do know the size. And so the implementation for that is going to say, okay, here's my size, and here's how to turn me into a list. And so the trace for that, you end up returning, okay, here's my size and a toList function. And it'll call the toList function, get back, here's the whole list of that enumerable, and then enum.slice will just take the items that it cares about. But then using stream again, if we try to slice it, it just says you're going to have to reduce over me. And so if we do that same range, turn it into a stream, and then try to slice off the second and third elements there, it is going to reduce over, drop the first one, take the second and third, and then halt with the items there. So that is how Enumerables implemented. Sorry, I got kind of into the weeds, but that's just kind of one side of the contract, you also have the enum functions that use that. And so I just wanted to trace like a map in enum versus a map in stream and kind of show how the same primitives can be used to kind of drastically do different things with it. And so for each of them, we're going to take the range 1 to 3, filter out any even numbers, and then toString it. And so if we do that with an Enum.filter, we're going to reduce over the thing, build up this list that ignores the 2 here, and then returns the list, and then reduces over the list to turn each item into a string. But then with stream, it like turns that into kind of a deeper call stack. And so it's the same thing. The stream is just there instead of enum. And now, hopefully that is very small, but I don't think I can make that bigger. So the filter map is going to call the call reduce on the stream, which is the filter, and then the filter is going to call reduce on the range. And so it'll ask, okay, what's my first item? And so the reducer passed by filter into range will be called with 1, and that reducer will say, okay, this is odd, I'm going to keep it, and pass it into the reducer for the Enum.map, and say, okay, here's an item, get back the ACK, return that, and then it'll say, okay, now I've got a 2, pass that to the filter stream, and that stream will say, yeah, you don't have a 2. And so it'll say, okay, here's your ACK. So it'll say, okay, I have a 3. That 3 will make it through the filter, get passed to the map, become the ACK, be returned to the range, and the range will say, okay, you've gone through all my items, I'm done now, here's the ACK. And the stream for the filter will say, okay, I'm done now, here's the ACK, and the function will have its result. And so I wish I could have dug more into maybe how that side of the equation works, but I think it's pretty neat how enumerables work. I have some links here. This is the blog post by Jose talking about the history of this. And then I have the enumerable tracer thing I built on GitHub, and then my company website. Yeah, thanks for having me.